Volume integrals, just like area integrals, one more step. So let's illustrate with an example. Integrating some function over a region. A region has no equations, has 3 parameters. So you're breaking this thing into little volume pieces. Sometimes it's hard to see because this is a typical way that the problem will be phrased. You use a region, inside, and then you have an equation. And you're like, oh, there's an equation. Nope, because it's inside. And it's above, and another equation. So it looks like there's equations. Those are surfaces, but they're the boundary of the region. So if I write out what the region is, it's inside, so less than or equal to, and it's above, bigger than or equal to. No equations, only inequalities. So I'm restricting the domain. Turn into polar coordinates. X squared plus y squared is r squared. So ZR plane is going to be nice. Change into spherical coordinates. Rho squared is r squared plus z squared. Z is cosine, and r is sine. Let's do the polar parameterization. Set up the ZR plane. Circle, radius 1. It's a half circle because r is always positive. Z equals r, it's a line. And theta swings that radial axis around. And there's my region. Fix 2 of the parameters, vary 1 of them. Almost always this is the way you're going to do it, is you're going to vary z. Almost always. Just the way the problems are set up. Just keep things simple. So z goes from r to, and I got to solve this for z. So there's my line integral. F is the height, dz is the base, and I'm summing over that line. And those lines exist over this region D. So D for the domain that these r theta points belong to. So we're using polar. So our z integral. And then dv is dz, r d theta. See what our domain D looks like. It's in the xy plane. When the upper and lower limits equal each other, I've pinched off my lines and I'm not summing anymore. So that's square root 1/2 or root 2 over 2 if you are using a slide rule. So it's a circle of radius root 2 over 2. So theta is my outer integral, r is my inner integral, z is my really inner integral, and I integrate. So the integrate first, integrate second, and then it's a calc 1 integral. Let's do the spherical parameterization. dv is rho squared sine phi, d rho, d phi, d theta. We do it in this order because almost always we're going to vary rho first. So draw our ZR plane picture again. But now we're going to do it in spherical, so I'm going to fix my angles. And I'm going to vary my radius. So there's our fixed angle, and our radius varies. So there's my line integral, going from rho equals 0 to rho equals 1. My ending of the phis, gotta solve this. In arctan, which is inverse tangent plus pi multiples. I'm in the first quadrant, so it's just inverse tan. my rho integral 0 to 1, my phis 0 to pi over 4, and my thetas. So I do the inside integral first. I'm integrating in rho. All the other variables are constants. So in particular, sine phi is a constant in this integral, and you can factor it out if you wanted to. Then second, you do the phi integral. And we're done.